Assalamualaikum warahmatullah and a very good day to our panels. Today our group will be presenting on our design project which is the production of 130,000 metric tons of nitric acid. Our group consists of 6 members which are Nurul Man Hakim, Nurul Afifah, Nur Izwa, Muhammad Ilyas, Wan Siti Aminah and Fatih Nurul Akilah. Nitric acid, which is also known as aqua fortis or spiritonator, is a monobasic acid. The pH of the nitric acid is 3.0 and they have a freezing point at negative 42 degrees Celsius and boiling point at 83 degrees Celsius. The industrial grade concentration of nitric acid came in 68%, while the 88% or higher nitric acid are called fuming nitric acid. Nitric acid is used by a producer of ammonium nitrate as demand for ammonium nitrate product, especially in fertilizer. Is also used in manufacture of explosive, dyes, coal tar product, drugs, and production of plastic. After the ecological comparison study between three different processes, child saltpeter, Berkeley and I, and Oswald process, the Oswald process was chosen as the product characteristic, show the efficiency and appealing result on the product quality, method applied, and environmental consideration. Our objective is to produce nitric acid that's suitable and high qualified for commercializing to the product market. Furthermore, nowadays, most industries prefer the Oswald process in producing nitric acid. For this production, it has been proposed to produce nitric acid by oxidation of ammonia process on a platinum and rhodium catalyst, as it offers more ecological advantages than another method. Ammonia and compressed air fed into the inlet stream for mixing purpose before being heated to 900 degrees Celsius in a catalytic converter reactor to form nitric oxide. The process stream is being cooled by passing through a cooler to 58 degrees Celsius or less. To form nitrogen dioxide, the nitric oxide react with oxygen in oxidation vessel. Then the product fed into the absorber for the third reaction happen where the nitric dioxide react with the water to generate nitric acid at 68% purity. In market analysis, about 133 tons was imported in 2017 and it was drastically increased in 2018 where about 1,144,000 tons was imported to Malaysia. Huge gap of import and export of nitric acid clearly show that Malaysia production of nitric acid is insufficient to fulfill the market demand. Therefore, this nitric acid plant will be designed to produce 130,000 tons per year in order to fulfill the gap of imported nitric acid in Malaysia, whereby to reduce about 1% of the total import. As for the raw material supplies, we just decide to get ammonia from the industrial company. The ammonia can be obtained from the Petronas Chemical Ammonia Sdn Bhd. And for the oxygen, we will obtain it from the Linden Gas Product Malaysia Sdn Bhd. We can see that the supply of the ammonia in Malaysia is sufficient to be supplied for our production of the nitric acid. Total of the capital investment is 66,446,000 ringgit Malaysia, and the product that we could achieve in year is 234 million ringgit Malaysia, and the annual profit per year is RM 188 million. As you can see, the break-even point is located at 12,000 metric ton as shown in figure 6. Within this point, the revenue indicates 25 million ringgit Malaysia. Therefore, the plant would make a profit stated if the sale of nitric acid linearly increase. It will generate a huge profit on 130,000 metric tons of nitric acid per year. The payback period of this plant is around 3 years to recover the investment cost as shown in figure 7. This production of nitric acid is estimated to have 10 years project life and prove to be viable and worth to invest.
Assalamualaikum. My name is Fatin Nur Akila binti Ishaq and I will presenting on chapter 2 site location. So for choosing site location for the production, there are some criteria that need to be considered, which are availability of raw material, which is oxygen and ammonia, utilities supply such as water supply and power supply, transportation facilities and accessibility, estimated labor supply that available in the area, environmental safety aspect, which include the buffer zone of the area from the community residential area, land availability and cost, which are the size of the land and the price that available, and lastly, the local community consideration must be given to the safe location of the plant so that it does not impose a significant additional risk to the community. The site location that has been chosen for the production of nitric acid is in Kerteh, Terengganu, Kemenang, Sarawak and Gurun, Kedah. From the table, the three site location that has been chosen, we have estimated land use for the production would be 20 acres, and Kerteh, Terengganu has the lower price, which is only 6 million. For the accessibility of the raw material, from the table, we can see that the oxygen and ammonia production is in Kerteh is the nearest to the site location compared to Sarawak and Kedah. For power supply, Gurun and Kerteh obtain from the Tenaga Nasional Berhad, while Sarawak will get the power supply from the Sarawak Energy Berhad. And the water supply will be obtained different accordingly to their state they are in, and the price range will be different. For labor supply, we have been doing research according to the 2019 unemployment rate for each state, and Gurun has the highest unemployment rate in 2019, which give a highest labor supply estimated for the production. Lastly, the primary buffer zone for the local community consideration, the site location must be located further away from the residential area. Site location in Gurun is far away from the residential area. After three site location has been chosen, we will be using the screening and scoring method to pick the best site location for the production of the nitric acid. On the left side is the screening table, and the right is the scoring method table. From the scoring method table, after comparison, Kerteh has been chosen for the production of nitric acid. The reason site location Kerteh is suitable for the production is because the site location it has lower land price compared to other two, despite having the same size of land area, and the production can save up to 78% for startup costs. Next factor is the environment aspect, where the site location is far away from the residential area by 6 km, which is much more safe for the community live there. Furthermore, the water supply in Kerteh, which is from the Syarikat Air Terengganu, has lower price range of tarif compared to the other water supply. The production can save cost on water supply by 36%. And lastly, the accessibility of the raw material. Location of production of the raw material is nearby to the site location by 2 km, and it can save time and cost for the transportation. That's all for me. Now we can proceed to the next chapter, which is mass balance.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Hakim bin Salih Rashid, and I will continue the presentation by presenting the new chapter, which is Chapter 3, Mass Balance. So before I proceed further on my presentation, I will briefly explain about the content for this chapter. So first, I will explaining on the choice of basis calculations. Second, I will explain about the assumption of the calculations for our mass balance. Third, I will show one of the example of the calculation for the reactive process. Fourth, I will also show one of the example of the calculation for the non-reactive process. And the last one, I will presenting on the overall mass balance. Before I proceed, I will do some recap on the mass balance fundamental. So as shown the equations inside the slides, the mass balance fundamentals is equals to the input minus output plus generation minus consumptions is equals to accumulations. So for the basis of our calculation, we assume 18 kmol per hour for the ammonia gas and 100 kmol per hour for the oxygen gas. The forward calculation will be performed in the calculation of our mass balance in produced nitric acids. There are a few assumptions of the calculation in calculating the mass balance, which is the first one. There will be one catalyst that we use in the reaction, which is platinum rhodium gauze catalyst. Second, we assume the conversion of ammonia to nitrogen oxide is 95%. Third, there will be no mass loss by the leakage of the equipment or piping. Fourth, we target the amount of nitric produced is equal to 130,000 tonnes per year, which is equivalent to 16,414.14 kg per hour. Next, we target the purity of nitric acid is 68%. And for our calculation in mass balance, the scale up method will be performed since the basis assumed are not achieve the target productions that we predicted. And the last one, for the reaction process, extent of reaction will be used in calculate the mass balance. In the production of nitric acid, there will involve three main reaction process, which is the first one is the oxidations of the ammonia, second, oxidations of the nitrogen oxide, and the third one is the absorptions of the nitrogen dioxide. So in this slide shows one of the example of the calculation for the reactive process which occurs at the ammonia converter reactor R100, whereby the oxidations of ammonia reactions happens. So the reaction occurs when the ammonia react with oxygens and producing nitrogen oxide and also water. So as mentioned before, we decided in calculating the mass balance that involve reaction process by using the extent of reaction method. The equation of the extent of reaction is Ni equals to Ni naught plus minus Vi multiplies with epsilon. So Ni is equals to the moles of the species I present in the system after the reactions occurs, and I naught the equals to mole of species I in the system when the reaction start. Vi is equal to stoichiometry coefficients for species I in the particular chemical reactions equations, and epsilon is the extent of reactions. So here are the example of the calculations of the extent of reactions that occurs in the ammonia converter reactors. Next, we continue with the calculation for the non-reactive process. So for the non-reactive process, the equation that will be used in calculating the mass balance is input equals to output, whereby when there is no chemical reactions occurs, the amount of the mass in will be equal to the amount of mass out. So here I show one of the examples of the calculation for the non-reactive process, which is occur at the mixer MIX 101. The input stream came from stream number 11 and stream number 13, and the output stream is stream 15. So in the box shows some of the calculations for the non-reactive process that occurs at the mixer MIX 101. For the last subtopic for this chapter, I will be presenting on the overall mass balance. As the figure shows in the slides, for the overall mass balance, it will involve 5 input streams and 3 output streams. Based on the calculation, the result shows that the amount of the mass flow rate for the overall mass balance is balanced, whereby the input mass flow rate is equals to 29,517.038 kg per hour, and the amount of output mass flow rate is 29,517.135 kg per hour. Next, we also perform and do the comparison of the manual calculations and the exponent HYSYS, and as overall, the percentage error shows for all streams were not exceeded more than 20%, which is the highest percentage error is at 17.884%, which is located at stream number 6, and for the lowest error is 0.229%, which is located at stream number 14.
Assalamualaikum, I am Wan Siti Aminah and I will be presenting energy balance. Table 7 shows the molecular weight and heat of formation value used in the calculation. The energy balance general equation is accumulation of energy in the system equals to energy flow into the system minus energy flow out of the system. For the main reactor where the reaction occurs, the heat of reaction needs to be calculated based on the stoichiometric equation. Heat enthalpy calculated using the heat capacity value. The effect of pressure drop are neglected as all the pressure difference are less than 50 bar. The reference state used is 25 degrees C and 1 bar pressure. The objective of energy balance is to know whether the system will need cooling or heating system, and other than that it will help to decide on what equipment that can be used. The first reactor is ammonia converter reactor where the oxidation of ammonia occurs. The inlet stream temperature is 534 degrees C and 7 bar pressure, while the outlet stream is at 900 degrees C and 6.5 bar pressure. The heat of reaction is equals to negative 71,294,054 kilojoule per hour. The sum of heat transfer is negative 16,479 kilowatt, which makes it an exothermic process. The oxidation of nitric oxide occurs at the second reactor called oxidation vessel column. The reactor consists of two inlet streams and two outlet streams. The oxygen inlet stream is 50 degrees C and 1.24 bar, while the other inlet stream is 50 degrees C and 6 bar pressure. Both outlet stream temperature is 56 degrees C and 1.21 bar. Heat of reaction for this process is negative 16,939,445 kilojoule per hour, with sum of heat transfer equals to negative 4,080 kilowatt. It is also an exothermic process. The third main equipment is combustion reactor where absorption of nitrogen dioxide occurs. This reactor consists of two inlet stream and two outlet stream. The water inlet stream condition is 30 degrees C and 7 bar pressure. Another inlet stream is 56 degrees C and 1.21 bar. Both outlet streams have the same condition, which is 82 degrees C and 1.16 bar. The process heat of reaction is negative 6,522,335 kilojoule per hour. The sum of heat transfer is negative 867 kilowatts, which also an exothermic reaction. Lastly is the overall heat transfer. The first two main reactors where the oxidation reaction occur, the heat transfer value from manual calculation and HISIS are almost the same. Ammonia converter reactor energy balance calculated is negative 16,479 kilowatts, while HISIS heat flow is negative 17,597 kilowatts. Oxidation vessel column heat transfer value is negative 4,080 kilowatts, and HISIS heat flow is negative 4,200 kilowatts. However, the third main reactor, conversion reactor, according to the heat of reaction value, it is an exothermic process. The manual energy balance calculated is equals to negative 867 kilowatts, but the HISIS heat flow value is 700 kilowatt, makes it an endothermic process. The rest of the equipment have a close value of heat transfer with the HISIS, except for the cooler and the conversion reactor. The overall heat transfer is negative 25,852 kilowatts. This process consists of a series of exothermic reactions. Mostly, cooling system is needed to cool down the outlet stream of the reactor. The heat obtained from the cooling system can be used as energy source using turbine. Another energy source for the plant is from solar panel.
Hi, my name is Nur Izwa binti Rahman, and I'm going to explain more on Chapter 5 Process Simulation. Equipment that involved with Penn-Robinson fluid package are oxygen gas flow splitter, gas mixer, ammonia gas and oxygen gas heater, cooler, ammonia gas and oxygen gas compressor. This type of fluid package also involved in the catalytic oxidation of ammonia with oxygen in order to yield nitrogen monoxide and oxidation of the nitrogen monoxide to produce nitrogen dioxide. For Peng-Robinson fluid package, the temperature involved in each reaction must be above negative 271 degrees Celsius and the pressure range is below 1000 bar. This type of fluid package is applied in basis 1 as it is compatible for reaction in the simulation that has pressure below 10 bar. Other than that, Peng-Robinson fluid package comprises of enhanced binary interaction parameters for all hydrocarbon-hydrocarbon pairs, as well as hydrocarbon-non-hydrocarbons binaries. Ammonia is classified as a hydrocarbon component as it is composed of hydrogen and nitrogen. The hydrogen is produced from hydrocarbon through steam reforming. This figure 14 and figure 15 here shows the decision tree for the selection fluid package of Peng-Robinson fluid package. Meanwhile, extended NRTL fluid package is applied in basis 2 as it is suitable for component in this simulation that has a wide range of boiling point. Equipment that involved with extended NRTL fluid package are water flow splitter, cooler, compressor, mixer, conversion reactor and absorber. This figure 16 shows the fluid package selection for nitric acid process simulation. Moving on to the next slide, we have this choice and sequence of the equipment. This figure 17 here shows us the HYSYS simulation process flow diagram for nitric acid production plant. Ammonia gas and oxygen gas feed into the inlet stream and being mixed in mix 100 before being heated to 900 degrees Celsius in catalytic converter R100 in order to form nitric oxide. The reaction occurs in R100 is known as the oxidation of ammonia. The process uses platinum radium quartz catalyst to enhance the reaction by determining the high conversion of ammonia. The process stream then passed through cooler E102 and E103 and cooled to 50 degrees Celsius. These two-stage cooler are implemented in order to prevent thermal shock as a sudden temperature fluctuation can lead to mechanical equipment failure. This E102 cooler is intended to reduce the temperature from 900 degrees Celsius to 400 degrees Celsius, while this cooler E103 is cooling down the gas from 400 degrees Celsius to 50 degrees Celsius. In order to form nitrogen dioxide, the nitrogen oxide reacts non-catalytically with oxygen in oxidation vessel R101. Then, the product feed into the conversion reactor V100 where the absorption of the nitrogen dioxide happens in order to yield the nitric acid. Nitrogen dioxide will react with water by absorption and producing nitric acid in aqueous form and nitric oxide as a vapor. The function of this V101 is to separate between the nitric acid and tail gas, whereby the tail gas will be out at the top stream and the nitric acid will be out at the bottom stream. Finally, the nitric acid coming out from the conversion reactor V100 and absorber V101 will be combined and mixed into the mixer mix 101. The purity of nitric acid that coming out from the mix 101 is found to be 69%, obtained from the simulation. The separation of nitric acid and tail gas occurred in absorber V101. The main purpose of this equipment is to separate or scrub the gas stream and remove all the impurities by trapping the components inside the gas stream with the falling liquid. The product stream of nitric acid after coming out from the absorber has presented a purity of approximately 68% after undergo the separation process. As you can see, the fluid flow principle is divided into three sections, which are heat exchanger section, reactor section and separator section. In heat exchanger section, the pressure drop is one of the important elements that need to be considered in the heater or cooler. The flow pressure at the beginning of a process is higher than at its end, and each heat exchanger has different value of pressure drop. From table, it can be seen that the pressure drop for the heater E100 and E101 are same, which at 100 kPa. Cooler E102 and E103 also have the same pressure drop value, which at 25 kPa. Moreover, the pressure drop for the E104 and E105 are 16 kPa and 70 kPa respectively. Next, for reactor section, there is an increasing of the temperature due to the reaction that occurs in production of the nitric acid as it is undergoing an exothermic reaction. It can be observed from the table that ammonia converter reactor R100, oxidation vessel reactor R101 and conversion reactor V100 undergoing an isothermic reaction, thus cause the temperature for each of these units to increase due to the reaction that occurs. Meanwhile, in separator section, the separator will help to increase the purity till reach the desired target of nitric acid. The main aspect that needs to be considered in the design of the absorber is the gas should be intimate contact with the liquid, plus with the effectiveness of the equipment will be determined of the production of the desired product. The separation process is happening when there's a lot of nitric acid gas produced from the conversion reactor enter at the bottom stream and the water is used as the liquid in the top stream.
Assalamualaikum, I am Nurul Afifah binti Zulkifli and I will be presenting about Chapter 6, Environmental and Waste Management. In this section, I will be covering on three major parts, which is wastewater management, waste gas management, and scheduled waste management. Generally, waste management is an act and practice that include disposal, transport, recycling or monitoring of waste produce, which is an effective instrument for mitigating the waste produce, enhancing the environmental condition and reducing water and energy consumption. Essentially, there are three types of waste produced from this nitric acid plant, which is first, wastewater. Wastewater is being generated from the reactor R101 at the bottom stream of stream 14 and consists mainly ammonia and other contaminants. Meanwhile, for waste gas is being emitted from the top stream of absorber, which is stream 27 and consists of nitric oxide and nitrogen dioxide. And lastly, for scheduled waste is being generated from the spent catalyst used, which is platinum rhodium catalyst, spent lubricating oil from the compressor, and other inorganic and organic constituents. Waste that produced from industrial process require act and regulation to monitor the impact that could cause pollution. The act and regulation that need to be complied for this nitric acid plant is Environmental Quality Act 1974, Environmental Quality Industrial Effluent Regulation 2009, Environmental Quality Scheduled Waste Regulation 2005, and Environmental Quality Clean Air Regulation 2014. There are specific limits for each parameter outlined in the 5th schedule of IER 2009. For this wastewater from the nitric acid plant, the parameter that being observed is chemical oxygen demand, suspended solid, oil and grease, pH value, and ammoniacal nitrogen. For the scheduled waste, it is stated in section 24 and 34b that to monitor the land from being polluted from scheduled waste or any chemical produced from the plant such as sludge. Meanwhile, for the Environmental Quality Clean Air Regulation, it is stated in the 3rd schedule of Regulation 13 the maximum exposure limit for nitrogen dioxide and nitric oxide is 700 mg per meter cube in a periodic monitoring. For the wastewater management, an industrial effluent treatment system (IETS) is designed to treat the wastewater by following the IER 2009. The main purpose of the IETS is to ensure that the wastewater contaminant follow the limit stated before being discharged to any sources of water. The figure shows that the design of IETS, which consists of primary, secondary, and tertiary treatment. For the primary treatment, screening, oil and grease trap, pH adjustment tank, and equalization tank is being used. In the meantime, for the secondary treatment, clarifier tank and aerated pond is being used to reduce the ammonia content in the wastewater. Lastly, for the tertiary treatment, media filter and carbon filter is being used to purify the wastewater before being discharged. The inlet flow rate of the wastewater is about 7,665 kg per hour. The figure shows the mass balance of the IETS is calculated, and it clarifies that the value of parameter of the wastewater effluent meet the standard A requirement in the IER 2009. Moving on to the scheduled waste management system, in this nitric acid production, scheduled waste need to be stored and treated properly according to Environmental Quality Scheduled Waste Regulation 2005. Each scheduled waste are coded differently according to its types and source point of the scheduled waste. For instance, waste catalyst, which coded as SW202, is generated from the catalytic converter, whereby the oxidation of ammonia occurs involving the catalyst of platinum rhodium. Next, waste sludge, which coded as SW204, is generated at the end of the catalytic converter, whereby the catalyst is formed in a solid cake. The spent lubricating oil, which coded as SW305, is generated from the machine that require motor or compressor, which used to smooth the process in the system. The last part of the waste management is the Air Pollution Control System, APCS. The objective of the APCS is to treat the waste gas before being emitted to the atmosphere. In this context, wet scrubber equipment is being used to convert the nitrogen oxide and nitrogen dioxide into nitrogen, carbon dioxide, and water by using the urea peroxide solution. As shown in the figure, the waste gas is being fed from the bottom of the wet scrubber, and the urea peroxide solution is sprayed at the top of the scrubber and react counterflow with the waste gas in the scrubber. Meanwhile, the nitrogen and carbon dioxide gas is released at the top of the scrubber. For the specification of the wet scrubber equipment, the length and diameter is about 1 meter and 0.4 meter. Meanwhile, for the efficiency of the wet scrubber is calculated and yield to 60.45%. As for conclusion, it is evident that our plant will obtain a huge profit, about 25 million ringgit, for 130,000 metric tons per year of nitric acid production, with the project life of 10 years and the payback period of 3 years. Apart from that, our site location, which is Kerteh Industrial Area, is found to be the strategic site location due to its cost of land, raw material availability, transportation, and water supply compared to other site locations. In addition, our waste management system, which is IETS, APCS, and scheduled waste, have secured the waste produced from the nitric acid plant and will not pollute the environment. Therefore, nitric acid plant is viable and worth to invest. That's all from us. Thank you.